Hello, everyone. Welcome to the April 21st edition of Math 371. Quick reminder, you have homework due on Friday. Today, we're going to talk a bit more about the matrix of a linear transformation. So in many ways, this is going to be a rehashing of some matrices that we've seen before. So the question you might be having is, why do we keep talking about these relatively abstract concepts that we've seen before in a more concrete setting? Well, in some sense, this is the essence of mathematics, where you take something you know, you generalize it to a more abstract setting, and you realize that this more abstract setting is more comprehensive than the easier setting you did before. And so it gives you more information and more power. Secondly, it's the goal of all math majors that you would be able to learn things that you haven't learned before. And so learning more abstract concepts is how we train you to have this ability that you can learn things that are not so concretely laid out. This will also help you as you go into logic and sets, if that's in your career trajectory, because that's a class where it's even more abstract than this. Okay, so let's begin. So the past couple lectures, we've talked about what it means for a matrix A to be diagonalizable. And we say that it's diagonalizable if there's a diagonal matrix D and an invertible matrix P so that A is P times D times P inverse. That's what it means to be invertible, to be diagonalizable. Now we're going to see what this means in terms of linear transformations. How does the transformation where you send x to A times x relate to the transformation where you send x to D times x? So that's what we're going to figure out today by figuring out what the matrix of a linear transformation is. Okay, so in this section, V is an n-dimensional vector space. And W is an m-dimensional vector space. And T is going to be a linear transformation from V to W. Remember, a linear transformation satisfies certain requirements like T of 0, the vector is the 0 vector, T of x plus y is T of x plus T of y, and T of C times x is C times T of x. So let's let beta be a basis for V and curly C be a basis for W. We're going to take a vector x, element of V, and recall that you can give the coordinates of x. So recall that the B coordinates of x are, it's a vector with n numbers in it. And if I plug my vector x into T and write that using C coordinates, it's a vector with m entries. So if this is my space V, that box represents the vector space V, and this is my vector x, we know that the linear transformation sends x to T of x, which is an element of the vector space W. Of course, let's let this box represent the vector space Rn. This dot is the vector x put in B coordinates. And here's the vector space Rm. Here is T of x. in C coordinates. Okay, so this puts a vector in B coordinates, and this puts a vector in C coordinates. And the question is, how do I go from the vector in B coordinates to the vector in C coordinates? So it's actually very easy to understand this relationship, but let's flesh it out first. So let's say that the vector, the basis B, has these n vectors in it. It's n-dimensional, the vector space V, so B must have the n vectors in it. So we know that the vector x must be some combination of these vectors, because that's what it means to be a basis. Here's some linear combination of them. So this tells us, well, I want you to think about it. What does this tell us that the vector x written in B coordinates is? So pause the video and think, what goes in that vector? Well, I think we all know what goes in that vector. It's just the coefficients on our basis elements, B1 through Bn. So let's take a look at what t of x is doing. That's t of this long expression. It's a linear transformation, so we can decompose this. And we can pull out the scalar. So what this is telling us is that if I write t of x in C coordinates, it's R1 times this vector in C coordinates plus R2 times this vector in C coordinates. Oops. All right. And so what we observe is that this image vector written in C coordinates is some matrix times xb, where we actually know what this matrix M is. You can trace the math and realize that it's these column vectors written together. And you know that each of these column vectors, so you see that there are n columns, and you've written this using the basis for C, so you have m rows. So you get an m by n matrix, big M. And we actually, this matrix M is what we call the matrix for T. This is the matrix for T relative to the bases curly B and curly C. So that's a definition. So that's a lot of abstract language. Let's give you an example so you know how to create this matrix. So let's let the basis B have these three vectors in it. We don't really know much about them, but we have three vectors. And we'll have the basis C for our vector space W with these two vectors. So this is a basis for vector space V, and this is a basis for the vector space W. And we know that T is a linear transformation from V to W. And we know the following. T of B1 is 3C1 minus 5C2. T of B2 is minus C1 plus 6C2. T of B3 is 4C2. So find the matrix for T relative to B and C. So go ahead, pause the video and try to calculate this matrix. All right, well, let's take a look at what this is going to be. So we need to write the vectors T of B in terms of C. So our matrix M should look like T of B1 written in terms of C, T of B2 written in terms of C, and T of B3 written in terms of C. However, we've already done that. The first one is just 3, negative 5. That's how we write T of B1 using our vectors C. And I think you'll see very quickly that this is our matrix. All right. So that was great. But let's specialize to a particular case that we're going to find useful, and that's linear transformations from V to V. That is, the domain and the codomain are the same. So we're going to let V and W to be the same and B and C to be the same. In this case, we simply call our matrix M the matrix for T relative to B, or we just call it the B matrix for T. Okay, so we know that it satisfies the following criteria. If you write T of X in basis B, it's this matrix times your vector written in B. So to give you a summary of what happens, if this is our vector space V, this is our vector space V, this is X, this is T of X, this is Rn, this is X written in terms of B, this is T of X written in terms of B, then to go from here to here is the matrix where you multiply by the B matrix for T. Okay, so let's do another example where we find the B matrix. So we have the following linear transformation defined by T of this polynomial is the following. First, we're going to find the matrix representation for T relative to B equal the standard basis. So let's see what that looks like. we need to write t of 1 using this basis, t of 2 using this basis, sorry, excuse me, t of t using this basis, and t of t squared using this basis, because those are the 3 basis elements. Well, we know that t of 1, okay, so let's take a look at 1. So 1 is equal to 1 plus 0 times t plus 0 times t squared. This is our a0 value, our a1 value, and our a2 value. So this becomes 3 plus 5t. So when I write t of 1 using this basis, it should be 3, 5, 0. All right, let's do t of t. So t is 0 plus 1 times t plus 0 times t squared. So that's a0, a1, a2. Okay, so this becomes 0 minus 2t plus 4t squared. And so t of t written in beta is 0 minus 2, 4. And last but not least, t of t squared is equal to 0 plus 0 times t plus 4t squared. So that tells us that when we write that in terms of the basis beta, we get 0, 0, 4. So what this is telling us is my matrix, B matrix for t, is just 3, 5, 0, 0, negative 2, 4, and 0, 0, 4. Okay, so I'm going to have you guys do an example where you find the C matrix for T, where T is the same transformation as above, where C is 1 plus T, 1 minus T, and 2T squared. So go ahead and use this to find the C matrix for the same linear transformation above. Okay, so now we're going to make a quick comment about linear transformations on your favorite space, n-dimensional space. Usually, T appears as a matrix. So, if we assume A is diagonalizable, then there is a basis of eigenvector, basis B for n-dimensional space consisting of eigenvectors of A. So that brings us to a theorem, which we're going to prove, called the diagonal matrix representation. So you suppose that your matrix A is P times a diagonal matrix times P inverse, where D is n by n diagonal matrix. Then if beta is the basis for Rn formed from the columns of P then the matrix D is the B matrix for the transformation X gets sent to AX. So let's prove this, and I think you'll see what we're saying. So let's let these vectors be the columns of our matrix P, and we're going to set B equal to the basis you get from that. So we know that the matrix P is just the matrix where you put your vectors B1 through Bn as columns. And this is the change of coordinates matrix. PB from chapter 4. So what this tells us is that P times a vector written in B coordinates is equal to X. And if you write your vector X in B coordinates, it's P inverse times X. So what this is telling us is that our matrix, our B matrix for T, is where we take each of our basis elements, plug it into T, and write it in B coordinates. And if we rewrite this, this is just A times B1 written in B coordinates. And this is actually the same as P inverse times A times B1 all the way up to P inverse times A times Bn. This is coming because we took this part and plugged it in up here. And so we can take it out of B coordinates and put it back. And so this is P inverse A times this, which is P inverse A P, which is our matrix D. And so we've shown that our B matrix is our diagonal matrix. So let's do an example so you can see how this all plays out. Let's let A equal this matrix, and T of a vector is just A times a vector. Let's find a basis B so that T of B is diagonal. Okay, so we know from the previous theorem that we just need to find the eigenvectors and use those. So we need to find the eigenvectors of this matrix. We need to take the determinant So this should equal minus 4 lambda plus lambda squared plus 3. And I believe that's lambda minus 1, lambda minus 3. So our eigenvalues are 1 and 3. So we need to find an eigenvector for each of those eigenvalues. So if we take 0, 1, minus 3, 4, we subtract off this. Okay, so that's the eigenvector where x and y are the same. So this should just be the vector 1, 1. We'll also subtract off 3. So this is the one where x is 1/3 of y. So that should just mean we can pick the vector, let's see, 1 and, 1 and 3. Okay, so this is lambda equals 1, lambda equals 3. Okay, so what do we know? Well, we know that the matrix P looks like this. And we also know that we can make our matrix D equals 1 and 3. And so A should equal P times D times P inverse. So let's check that that's true. So P is 1, 1, 1, 3. Diagonal matrix is 1, 0, 0, 3. And P inverse, let's see, that has determinant. This is determinant 1. So it's 1/2 times, let's see, switch them, minus, okay. So this should equal 1, 3, 1, 9 times 1/2 times 3, -1, -1. Okay, so it's 1/2 because that's, so that's 0, 1, 2, minus 6, 8, which is 0, 1, -3, 4, which is A. Excellent. So we found our matrix P, and we know that using this basis, so this basis, that D is the B matrix for x goes to AX. And so we've found the basis that we want. All right. Last section for today, similarity of matrix representations. Okay, so the proof of the previous theorem did not use the fact that D was diagonal. Therefore, what does this tell us? If A is similar to a matrix C, e.g., A is P, C, P inverse, then C is the B matrix for X getting sent to AX, where B is formed from the columns of P. So let's summarize this in a diagram. If this is our vector x, and we're sending it to ax, when you multiply x by p inverse, this sends x to x times x written in beta coordinates. You multiply this by p, you get ax in beta coordinates, and this matrix here is C. Sorry. Okay. Conversely, if T goes from Rn to Rn, is defined by T of x is Ax, and B is any basis for Rn, then the B matrix for T is similar to A. So this is telling us that the B matrix of a transformation is similar to the matrix, to the matrix that defined the transformation. So what is this telling us? The conclusion is that the set of all matrices similar to A coincides with the set of all matrix representations of the transformation where you send x to A times x. Okay. So I'm going to give you guys a problem to work on, and we'll have more problems to do in class. But this will be a good one to work on to make sure that you know what the concepts are and how to make your calculations. So let's pick your matrix A equal to this expression, and your basis B is given by these vectors. And we define the transformation T by T of x is Ax. I want you to find the B matrix for T. All right, let me know if you have any questions. See you in class.